Hi everyone, let's do some more chi-square tests. And these are also going to be right-tailed tests. This time we're going to talk about chi-square tests for dependence or independence. Are two variables statistically related or not? Actually, if the variables are statistically related, that's the case of dependence. Now, we've dealt with two-way frequency or contingency tables before. For example, when we talked about the tutor who was interested in working with students who were B students or C students or juniors, we've dealt with these kinds of tables before. Now, in example one, we're going to consider two variables in an election, gender and party preference among registered voters. So over here, let's say we take a poll of 700 voters. And let's say that each voter can either be a gray party member or a yellow party member. For the sake of convenience, let's say these are the only two possibilities, the only two values for this variable. Likewise, let's assume that there are only two genders, men and women among adults. I realize that's very controversial. I know on Facebook there are hundreds of genders. But let's assume that we have the two genders here. Now we're asking not so much directly men versus women or gray versus yellow. Really, we're asking more about the relationship between these two variables. Although it is true that in the 2x2 case, this really does boil down to a test for two proportions. That is actually true. Right. All right. Now, two variables are independent if and only if there is no statistical relationship between them. Otherwise, if there is a statistical relationship between them, they are dependent. Now, that's different between causality. There's a difference between dependence and causality, and we'll talk about that later on. Also, let's quickly review the idea of independence. In both two-way tables below, it appears that gender and party preference are independent, meaning that knowledge of a person's gender gives you no additional information about the person's party preference, and vice versa. So remember, back when we were talking about probability, if I took one card out of a deck of 52 cards, and if I told you the rank, for example, this card is a 4, did that give you any additional information about the suit, whether the card was hearts, diamonds, clubs, or spades? If I just told you the rank, the card's a 4. The answer is no. Knowledge of the rank gave you no additional information about the suit. The suits were still 1/4 apiece in probability. So there was independence between rank and suit, at least on the first draw. Now I claim that in both 2x2 contingency tables below, gender and party preference seem to be independent, or at least there's no evidence against dependence. There's no evidence against independence. There's no evidence against independence. So for example, over here, does knowledge of gender tell you something additional about party preference? Well, no, because it looks like the gray party is doing very well. In fact, exactly a 2-to-1 margin in both groups, men and women, based on the sample. If I told you the party preference, would that say anything more about gender? Well, no, because the gray voters are equally split between men and women, but so are the yellow voters. They're also equally split between men and women. So this is a case where there is no evidence whatsoever against independence. This table perfectly reflects independence between the two variables. Knowledge of one tells you absolutely nothing about the other, even in just a sample. Now here, we had equal numbers of men and women, but you didn't even have to have that to be the case. For example, here, this might be the ancient Amazons. There were literally 10 times as many women as men in this sample here, okay? But still, we have independence. Again, this table here perfectly reflects independence. Because in both groups, the gray party is beating the yellow party by a margin of 2-to-1. And for both parties, with the gray party members, women outnumber men 10-to-1, but that's also true among the yellow party members. It's 10-to-1. So knowledge of the value of one variable gives you no information about the other variable and what value it could be. There's no additional information. By the way, we call these 2x2 tables. We don't count the marginals here. These are called the marginals, the row totals here and the column totals here. This is the grand total here, which corresponds to all the frequencies in the 2x2 table here. Okay. So let's take a look at this table here. Let's take a look at this table here. Wait a minute. Now, if I tell you what gender the person is, for example, if I say that gender is a man, the gender is male, well, that person is 5 to 1 likely to be for gray. 5 times as likely to be for the gray party as for the yellow party. But if I tell you the person is a woman, that person is 5 times as likely to be for the yellow party. So if I tell you that gender, that can tell you something about the party preference in terms of probabilities. If I tell you that the person is a gray voter, then there's a 2 to 1 chance that person is a woman. If I tell you that the person is a yellow voter, wow, there's a 50 to 1 chance that the person is a woman. Now, in both cases, there are more women than men. I mean, still, it's like the Amazons. There are 10 times as many women as men. Whether I tell you that I have a gray voter or a yellow voter, you're more likely that the person's a woman. But here, the margin's only 2 to 1 among the gray party members. Here, it's 50 to 1 among the yellow party members. So it matters. Knowledge of the value of one variable can give you additional information about the other variable and what value it could be. Next, we will actually discuss a particular example, setting up and conducting a hypothesis test, the chi-square test for independence or dependence. Next.